Welcome to another episode of UnpackAI. Today, we are diving deep, and I mean deep, into a model that's really shaking up the open source AI world. We're gonna unpack the nuts and bolts, the architecture, the training of the absolutely groundbreaking Kimi K2.
Okay, let's just start with a number that kind of sets the stage here. 1.04 trillion. Yeah, you heard that right. That is the total number of parameters in the Kimi K2 base model. It is easily one of the most ambitious open-weight models ever created. But, a big number is just that, a number. The real story, the interesting part, is how on earth you build something this massive, and maybe more importantly, what you even build it for.
And that right there brings us to the absolute core challenge of this whole thing. See, training a model at this scale, it's notoriously ridiculously difficult. They are so prone to instability, to failures that can just completely derail a project for weeks, wasting tons of money and time. So the big question is, how did the team behind Kimi K2 manage to tame this trillion parameter beast? Well, let's find out.
All right, so first things first, we really need to get our heads around Kimi K2's design philosophy, because it wasn't just built to be big for the sake of being big. No, it was built to be an agent. It's designed to go way beyond just answering your questions and actually do stuff, to perform complex, multi-step tasks out in the real world.
And the core idea here is what they call agentic capability. So think of it less like a simple chatbot you ask questions to, and more like an autonomous assistant that can actually use software, browse the web, and interact with all sorts of systems to get a job done. It's not just about what it knows, it's about what it can do. It's about action.
And this design choice, it has a very real, practical result. Kimi K2 can handle somewhere between 200 and 300 tool calls in a row, completely on its own, no human intervention. Now, to put that in perspective, most other models start to lose coherence after just a few dozen. This kind of capacity opens the door to some seriously complex autonomous workflows, like having it conduct in-depth research for you. So how did they pull this off? Well, it all starts with the training foundation. And this brings us to one of the absolute biggest hurdles they had to clear: training stability. I mean, think about it. You're trying to train a trillion parameter model on over 15 trillion tokens of data. You just can't afford a single failure. A crash could be catastrophic. To solve this, the team came up with a brand new, novel optimizer. That optimizer is called Muon Clip, and it's a really clever piece of engineering. It basically combines an efficient algorithm called Muon with this critical safety feature they developed called QK Clip. Now, what does QK Clip do? You can think of it like a governor on an engine. It's there to prevent certain internal calculations from just spiraling out of control and blowing everything up. And this combination is what allowed them to train Kimi K2 for months on end without a single catastrophic failure. That's huge. So, on the left here, you're looking at the absolute nightmare scenario of large-scale training: instability. There's this key internal calculation, don't worry too much about the name, attention logits, that can literally explode numerically. Just poof. And when that happens, the whole learning process fails. On the right, though, you see the beautiful solution that Muon Clip delivers: pure, simple stability. So let's actually see what those exploding logits look like in practice. Okay, this is what instability looks like. In a test run they did without Muon Clip, the maximum value of those attention logics just shot past 1,000 almost instantly. The engine analogy is perfect here. It's like the RPMs on your car going way, way into the red. It's a clear sign of impending catastrophic failure. This kind of numerical explosion can cause the entire training run to just diverge and crash, wasting literally millions of dollars in compute time. And now here's the solution in action. During the actual Kimi K2 training run, that QK Clip mechanism put a hard cap on those same logits, right at a value of 100. You can see it, the value hits that ceiling and just stays there, perfectly regulated. It's a pretty simple idea, but it's an incredibly powerful innovation that provided the rock-solid stability they needed to build this entire model. Okay, so now that we get how they kept the training from blowing up, let's pop the hood and take a look at the model's actual architecture. Because a trillion parameters doesn't mean it's just one single monolithic brain. Nope, it's something much, much smarter and way more efficient. So Kimi K2 uses what's called a mixture of experts, or MoE architecture. And the idea is brilliant. Instead of firing up all 1.04 trillion parameters for every single token it processes, it intelligently routes the information to just a small subset of expert networks. The analogy they use is perfect.
Imagine a team of 384 specialized consultants. For any given problem, you don't talk to all of them, you just call on the 8 most relevant specialists. This gives you the raw power of a massive model, but with the computational cost of a much, much smaller one. It's the best of both worlds.
Let's dig into the specific design choices a bit. If we compare it to another really powerful model, DeepSeek V3, you can see Kimi K2 has more total parameters and way more experts, 384 of them. But here's the kicker. Notice the activated parameters are actually lower. What does that mean? It means it's even more specialized, or sparse as they call it. They also made a really interesting choice to have the number of attention heads down to 64. That was a key decision to make processing faster, especially when you're feeding it really long inputs. So why the magic number of 384 experts? Well, it wasn't a random guess. The team's research actually uncovered something they call a sparsity scaling law. What this chart shows is pretty cool. For the same amount of computation, so the same cost, as you increase the number of experts, which makes the model more sparse, the model's performance actually gets better. You can see that here with the lower validation loss. So they settled on a sparsity of 48, which works out to 384 total experts with 8 of them active for any given token, as the perfect sweet spot, balancing those performance gains against the sheer complexity of the infrastructure. All right, so we've got this stable, super efficiently designed model. But all that raw pre-trained power isn't enough on its own to create a truly capable agent. The next phase is where the magic really happens. This is all about teaching it how to reason, how to plan, and how to actually use tools.
To teach this thing how to use tools at a massive scale, they built this incredibly sophisticated data synthesis pipeline. It's a 3-step process. First, they create a gigantic library of tools, both real and synthetic. Then, for those tools, it generates all sorts of hypothetical agents and tasks. And finally, it actually uses other AI models to generate successful examples, they call them trajectories, of these agents solving those tasks. The result is a huge, super high-quality dataset that's purpose-built for teaching the model how to act. Now, after that initial training, its skills are sharpened even further with reinforcement learning, and they do this in a few cool ways. For objective stuff, like coding, it learns from very clear rewards. Did the code work? Did it pass the tests? Simple. But for more subjective tasks, like writing, it learns to critique its own responses against a really detailed rubric. And for coding specifically, they use a hybrid approach that combines scalable simulations with real execution sandboxes. This makes sure the skills it learns in training are actually effective in the messy real world. Okay, we've covered a lot of ground. We've talked about the stable training, the super sparse architecture, and the agentic post-training. So now, for the moment of truth, let's see what this all adds up to. How does Kimi K2 actually perform on some of the toughest, most grueling benchmarks out there? Let's start with SWE-bench. This benchmark tests a model's ability to fix real-world bugs pulled straight from GitHub issues. And Kimi K2 scores an incredible 72.5. Now, that number might not mean much on its own, but look at the comparison. It significantly outperforms some of the most powerful closed-source models out there, like Claude 4 Opus and GPT 4.1. This just screams top-tier coding and reasoning ability. And that trend just continues on LiveCodeBench. This is a benchmark for those really tough, competitive programming problems. And what do you know? Kimi K2 again takes the lead. This just reinforces its absolutely advanced capabilities in logical reasoning and code generation, which, by the way, are the foundational skills you need for a truly powerful agent. And hey, it's not just about these automated benchmarks, right? Let's talk about the LMSAS arena. This is where thousands and thousands of real users vote on anonymized AI outputs. They don't know which model they're talking to, and in that blind test, Kimi K2 was ranked as the #1 open source model. That's huge. It shows its power isn't just theoretical. It translates into generating responses that real people actually prefer. So let's just quickly wrap this up and summarize. Kimi K2's incredible success really rests on 3 key pillars. First, you've got the Mu-on-Clip optimizer, the secret sauce that made stable training at this crazy scale even possible. Second, there's that ultra-sparse and super efficient mixture of experts architecture. And third, that very deliberate and sophisticated post-training process that was all about creating true agentic intelligence. And all of this brings us to a final and, I think, really crucial question. All the innovations we've talked about today have produced what is undeniably one of the most capable open-weight models to date. So as this level of agentic power becomes more and more accessible to developers and researchers everywhere, it really forces us to stop and imagine what's next.
What new tools, what new businesses, what new scientific breakthroughs are now suddenly possible? Subscribe to stay connected for our next Unpack AI video, and comment below what made Kimi K2 stand out for you.